Good afternoon and welcome everyone to our second webinar of 2025 for the Strong Foundation Professional Development for Geotechnical Engineers. So this is a non-technical webinar series by the Young Professionals Committee of the Canadian Geotechnical Society. My name is Leonardo. I am a graduate student in Geotechnical Engineering at Western University in London, Ontario. Thanks everyone for joining us today. I want to take a moment to tell you about the Young Professionals Conference. It's happening in September this year in Manitoba, right before the national conference. I'm going to type in the Q&A the link. The registration got extended until next week. So if you guys are interested, please check that one up. Some housekeeping items. If you have questions to our speaker, please enter them in the Q&A field. And then if we have time at the end, I'm going to read the questions out loud. And then lastly, we do have a LinkedIn group that you guys can join. It's called CGS Young Professionals Committee. And there you can keep up to date with the initiatives such as conferences, meetup, networking events, and so on. So with that said, it's my pleasure to introduce our speaker for this webinar. Lucy is Senior Geotechnical Engineer and Senior Principal at Stantec in Calgary, with over 30 years of experience. She is a geotechnical, mining, slopes, and dams specialist and has worked on projects in US, Canada, Europe, Australia, and South America. Lucy is a member of 2 geotechnical review boards. Lucy loves working on challenging technical projects and solving problems in teams of talented people, some of whom are developing and growing their talents. It's what makes work engaging and interesting. Lucy has a keen interest in human factors and has previously presented on the subject in Tailings and Minewaste and CDA conferences, as well as to specific owner groups, such as Suncor and Ontario Power Group. She's a member of the Canadian Dam Association Working Group, looking at functions, failure modes, and failure mechanisms, and from 2020 to 2024 was an advisor on the Women in Mining Calgary board. Outside of work, Lucy enjoys spending time with family, friends, and her 2 golden doodles. She loves to ski, hike, bike, plan vacations, and play pickleball. Please join me in welcoming Lucy Phillip.
Thanks very much, Leonardo. So I'm here to talk to you today about human factors in geotechnical engineering. I've set up a little agenda. I'm going to go through how I started this journey, what human factors are. I'm going to talk about heuristics and then the expert halo. I'm going to talk about cognitive bias and then what we can learn from other professions and groups and what we can do to reduce the impact of human factors in our geotechnical practice and where we can get bias creeping in geotechnics. But I'm going to then conclude and we should have time for questions, I imagine. Oh, sorry, I've heard my screen isn't sharing. Sorry, I think when the meeting got changed, it flipped my screen.
It's on now.
Okay, it's on now. So back to the agenda. That's what we're going to talk about today. As Leonardo mentioned, I'm kind of quite passionate about this topic, so I'm excited to talk to you about it today. So how did I get kind of passionate and excited in this journey? Looking into human factors. It started in about 2018, 2019, when I read all these headlines. It was a bad snow year. And I read all these headlines about people dying in avalanches. And it was kind of interesting because when you look into these avalanches, like there were 2 US ski team members that died. You can see from the top headline that those missing were highly experienced climbers. So it tended to happen to experienced people rather than less experienced people. And so experienced and qualified groups, so come to avalanche hazard, despite the fact they had really sophisticated equipment, like we do in geotechnical engineering, good technology, like we do in geotechnical engineering, and they had a lot of training. In fact, the higher level of training you had and the higher level of education, you're more likely to die in an avalanche if you go into the backcountry than those with lower levels of education, which is kind of interesting. And in fact, with the terrain, if you're very familiar with the terrain, again, you're likely to have a higher chance of dying, 4 times more likely to die in familiar terrain than unfamiliar terrain, which is also interesting. It kind of brings in a complacency question. So I wondered whether there was, anything we could learn in our practice from these kind of avalanche incidents where highly skilled people were making mistakes and dying. And in 2004, a researcher in the backcountry, McCammon, he got fed up with having all his friends die. So he reviewed 715 backcountry incidents and accidents and introduced the concept of human factors, which is how he answered the question, how do people come to believe a slope is safe even when they're faced with likely evidence it isn't? And that's similar to us in geotechnical. We can make mistakes even when we're faced with evidence that is to the contrary. So before we delve into a bit more detail, I'm just going to talk about what human factors are. Human factors refer to environmental, organizational, and job factors, and human and individual characteristics which can influence behavior that affect health and safety. That's the definition out of the UK, the Health and Safety Executive in the UK. Human factors are the people elements of individual and system conditions that influence performance and reliability. And the WHO, the World Health Organization, recognizes that human factors apply wherever humans work, wherever they work. And they found that the perfectibility model, which assumes if workers care enough, work hard enough, and are well trained enough, errors won't occur, is untrue and counterproductive. So human factors range from the way we review evidence, we make decisions, approach risk, have social pressures, errors, work cultures, and whether the systems or company systems or mentoring help prevent human factors. But we need to prevent complacency and remain vigilant. So there are a few different categories here of human factors. I'm only going to consider really these ones today, a bit about behavior, non-technical skills, teamwork, a bit about culture, a lot about decision-making and communication. And really I'm going to focus on human factors that are heuristics, expert halo, and cognitive bias. And I'll go into each of those. So what are heuristics? Heuristics are simple, efficient rules of thumb or mental shortcuts that are instilled by evolutionary processes. So they're the way in the far distant past we dealt with these sort of unpredictable environments, and we had to make decisions quickly. So we created these mental shortcuts. And they explain how people make decisions, judgment, and solve problems. Typically when facing complex problems or incomplete information. And they were developed evolutionary in evolution, so they can work well and they ease our cognitive load, but they can also lead to errors and cognitive biases, especially when we use them instead of analytical thinking in unpredictable high-risk environments. So they can lead to common decision-making flaws. So usually there's some sort of pattern recognition that is going on in our subconscious mind. So we have sort of some haphazardly gathered data. We have some kind of prior experience, and unconsciously we judge that in some manner. But that reasoning, that informal reasoning, can be fallible and can lead you to unconscious bias. So one heuristic is the expert halo, it's called, and it's worth digging into a bit further, as it's to do with experts, and we rely on experts in our industry, so it's worth digging into. And the Dunning-Kruger effect relates to self-assessment. So in 1999, they produced this little chart on the right of the slide, and you can see on the y-axis we have confidence, how much we think we know, low at the bottom, high at the top. And on the x-axis we have competence or experience, however you want to interpret that. So that goes from low to high. So when you start out on something, you're actually pretty confident. You're pretty confident you can tackle it until you get to the point called the peak of Mount Stupid, or the peak of stupidity, when you're sure you know a whole lot and you're feeling really great about it. But then you realize actually how little you know, and you slide down in confidence into the valley of despair, which is also known as insecure canyon. And down here, you're embarrassed about how little you know. And then when you realize how little you know, that's the first step to becoming someone who actually knows stuff about something. And so you climb up this slope of enlightenment until you reach the plateau of sustainability. So when you're really experienced, you'll be on this plateau. But interestingly, your confidence never recovers back to where it was. So you're on the peak of Mount Stupid. And that's because people who know very little about something often think they know more than they do, while experts are more aware of what they don't know. So you never quite get it back. And you can cycle along this path, like this time column and this time axis, the x-axis. You would come along this path at different rates based on your individuality. And there are things you can do to drive yourself along this path, but they need recognition that you need to drive yourself along this path. So in summary, Dunning-Kruger, these two researchers, came up with people tend to overlook their own weaknesses and overestimate their own abilities. And people value their own contributions in a biased way. We all think we've got a lot to offer, and we're probably one of the best people for the job. But in reality, that can't be true for everybody. So people tend to think they're more skilled and less risky than others. So for example, research out of the US shows that 93% of US drivers believe themselves to be more skillful than the average driver, which clearly can't be true. John Cleese, the British comedian, said, if you're really, really stupid, then it's impossible to know you are really, really stupid. I think that's a bit of an exaggeration, but that refers to the Dunning-Kruger effect. So that's linked to the expert halo, because experts can be hard to spot. They're hard to spot because confidence is not related to expertise. And when you have blind trust in a more experienced partner, that's called the expert halo. So it can be dangerous because people perceived as experts can dominate decision making. And also experts can drift outside their realms of expertise. That's happened in a couple of high profile failures where people are experts in one thing, but they sort of drift outside of their expertise, and people are carried along on that journey with them and suddenly believe they're experts in everything, and so believe what they've said. So that can be a bit dangerous. And of course, like all of us, experts are subject to heuristic traps. No one is exempt from heuristic traps. So the other one, which can stem from heuristics, is cognitive bias. So it's a systematic error resulting from the use of heuristics, emotions, motivations, or social pressures. And cognitive bias is are systematic patterns of deviation from rationality, and they occur because of how our brain works. So we have a systematic tendency to engage in erroneous forms of thinking and judging. Cognitive bias was first introduced by a couple of researchers in 1974, and it's known that everyone exhibits cognitive bias, and no one is exempt. It's not based on how intelligent you are or how experienced you are. No one is exempt from cognitive bias. And they affect the way we evaluate, interpret, judge, and use and remember information, and how we make decisions. So cognitive biases can cause us to be irrational in the way we search for, evaluate, interpret, judge, use, and remember information, as well as the way we make decisions. Our biases sort of came to us because in an evolutionary manner, they can increase our mental efficiency. We can turn them over quickly, but they can distort thinking and lead us to this poor decision-making and false judgments. Heuristics and cognitive bias are related terms. So the heuristic is the rule or strategy or mental shortcut, whereas the systematic error that results from using a heuristic is called a cognitive bias. So they're connected. So here are a few cognitive biases, and I'm going to show a few on the next few slides and just tap into a couple in a bit more detail. So the first one's anchoring bias. So that's when people are over-reliant on the first piece of information they hear, and they weight that more accordingly than later information. I'm just going to chat about the ones that I think perhaps have a little bit more relevance in geotechnical engineering here. So availability heuristic is where you overestimate the importance of the information that's available to you. The example they give here is that a person might argue that smoking is not unhealthy because they know someone who lived to 100 and smoked 3 packs a day. So you overestimate what's in front of you and underestimate what isn't in front of you. One I think that's common to lots of professions and geotechnical as well is the bandwagon effect. This is also known as groupthink. It's the probability that you'll adopt a belief that will be increased probability based on the number of people that hold that belief. You have security in numbers, so you tend to jump on the bandwagon. And another one is confirmation bias. I think that can be quite common. We tend to only listen to information that confirms our preconceptions. So we might have some kind of theory or geological interpretation, and we tend to close off other evidence and only think about the evidence that supports what we want to say. Conservatism bias is where people favour prior evidence over new evidence or information that has emerged. I kind of see that quite a lot in geotech. You know, I review lots of reports or third-party reports, and I see that someone adopted parameters back in 1984, and since then there have been 2 or 3 rounds of drilling and lab testing, but the parameters have stayed the same, and that's because of confirmation bias. They get grandfathered in. A couple of other ones to talk about. Information bias. This is the tendency to seek information when it doesn't affect your action. So I think that would relate to geotechnical engineering in terms of the investigation that you're going to do, or the instruments that you're going to put in the ground. So if you're monitoring something, you should be monitoring for a reason, not just a sort of scattergun approach. An ostrich effect is where you ignore dangerous or negative information by burying your head in the sand. So that might be ignoring outliers in your lab testing data because you don't believe they're representative. So you need to be a bit careful about that. Overconfidence, I've talked about this really with the expert halo. You know, you have to be careful that you don't interpret confidence as expertise. And recency, which is the tendency to weigh the latest information more heavily than older data. I've definitely seen that. If old data perhaps has low strength data or something like that, but the latest data shows it's all better, it's very easy to assume that the latest data is the only data that counts. So it's worth digging into other professions and groups and learning what they know about human factors and what they're doing to prevent human factors in their work. So in the US, the third leading cause of death after heart disease and cancer is medical error. It's estimated it causes around $250,000 deaths per year and costs around $20 billion US. Human error is inevitable, and although it can't be eliminated, we can better measure the problem, define safer systems, mitigate its frequency, visibility, and consequences. So they've done lots of work into the role of cognitive bias recently, and they found that all clinical decision makers are at risk of bias error. Everybody. And doctors ranking themselves when they asked doctors to self-assess whether they were free from bias. Those that said they were free from bias actually scored poorly for biases. So everyone has it. You can't pretend you don't. And if you think you don't, you're wrong, is the conclusion there. So they've put some strategies in place. They try and make their errors more visible so their effects can be intercepted. So that would be akin to monitoring in the geotechnical world, I think. They have remedies at hand to rescue patients. So that would relate to emergency planning, perhaps like in dam safety, being able to implement an emergency plan. And they recognize that these human biases can happen, and they put systems in place that help reduce them. They also have safety triggers to alert staff. So that, I think, would be akin to a trigger action response plan in the geotechnical world, where you observe something. You know that if you're observing something and it triggers an alert, you're going to do something about it, and you know what you're going to do about it. And they've also facilitated a culture of speaking up, which is important as well. I'll go into that a bit later. So they've looked at the role of cognitive bias, and they've found it doesn't correlate with intelligence or any other measure of cognitive ability. Everybody has it, and up to 75% of errors in internal medicine are thought to be cognitive, and they happen at all steps in the medical process. The four main ones: overconfidence, tolerance to risk, anchoring. Five main ones: information and availability biases are associated with around 40 to 80% of those error cases. So here are a few of the biases that are pretty common in the medical world. So there's anchoring, which is where you cling to your initial impression, even as conflicting and contradictory data emerges. I talked about grandfathering in parameters or interpretations earlier, and that would be an example of that. I'm not going to go through all of these, but I'll talk about a couple. So diagnostic momentum, which is where you continue a course of action instigated by someone else without considering the information available and changing the plan if required. I definitely see that in geotechnical engineering on projects that have been started and stopped and delayed a few years and changed a little bit. It's easy to just carry on as before without sort of starting again. The framing effect is interesting. That says that we react differently depending how information is presented to us. And search satisfying is interesting. That's when you stop looking for further information or answers when you found your first plausible solution to the problem. And search for supportive evidence. That's where you interpret information to fit a hypothesis rather than the converse, rather than coming up with your hypothesis based on the information. That's also known as cherry picking or confirmation bias. In the maritime industry, they've long since recognised, since the mid-90s, that human factors are an issue for them, and they're to blame for 80% of oil spills and marine accidents. They found they're the root cause of most casualties, and therefore they've worked out that it should be the target of safety and prevention programs. They found out in their research that people tend to ignore information consistent with their beliefs until it becomes irrefutable. So they won't change their mind unless faced with irrefutable evidence. And that's been cited as a cause for unrealistic optimism, where accident risks are characterized by uncertainty, because people don't intervene until it's too late to intervene, because they just simply won't change their mind about their beliefs. Commitment or goal blindness is found to be an issue. So that's where you're focused on the end result, and all you're doing is focusing on getting to the end result that you want to get to, and you kind of ignore things on the pathway. And they found as well that when you're pushing a system to the limit, if you have a high staff turnover, that can be problematic and cause more human factors. In the backcountry, so this is what started me on my journey, there's been a lot of research into human factors, and it appears in any kind of avalanche book that's up to date now for backcountry users. Backcountry is what's known as a poor feedback or wicked learning environment. And I think geotechnical engineering can be that too. That's where we have illusions of skill, and we mistake good luck for good decision making. So these poor feedback environments have no immediate feedback on the decision making process. And if nothing bad happens, we tend to evaluate our decisions as the right ones, not because those decisions were good, but because we didn't receive feedback that they were bad. So you might go into the backcountry on a high risk avalanche day, you go into the terrain, you come out alive, and you think you made the right decision. And that might not be the case. You might have just been merely lucky. So that can cause this loop where we inadvertently form inaccurate assessments or develop potentially dangerous habits based on poor decision making. I think that can be definitely true in geotechnical engineering. We don't see a lot of the geology or the ground that we're dealing with, and I think it's very easy to walk away thinking we're very good at something when actually we might have just been lucky. And so a good quote from the literature is, competence often leads to success, but success itself does not indicate competence. So a bit like the medical profession, there are quite a few cognitive biases that are prevalent in the backcountry industry, and I'll pick out a couple of these maybe. We've talked about the expert halo. Familiarity or complacency, I think that's one that really comes into sight. Health and safety is believing a course of action is correct because it's been done before without incident. I think that's also possible in design situations as well. Social facilitation, which is believing the action is correct because others are doing it. That's also known as the herding instinct, groupthink, safety in numbers. Search for supportive evidence was one that they had in the medical world, where there's a willingness to gather facts that lead to your preferred conclusions and disregard facts that threaten them. This is just a little bit of a slide from soccer, the previous England football manager. And this is a quote from a book by Syed that I like. There's one universal truth about human psychology. We love being surrounded by people who think just like us. However, that means we have similar concepts, heuristics, and models. And the previous England football manager in his first Euro campaign did incredibly well. And he had recognised that, and he developed an advisory board that comprised people from different diverse backgrounds. He recognised their different experiences would contribute to solving problems and having a pathway forward. So he surrounded himself by rebels that inject a sense of fresh thinking and help everyone perform better. So on the right, you can see his advisory board had a cycling coach, a military college commander, an Olympic rower, a tech entrepreneur, and a rugby coach, because he felt they all had something to offer in terms of improving performance. So he developed this board with divergent thinking rather than the convergence of echo chambers. And echo chambers may be comfortable, but they're inherently self-limiting. So this speaks to having an environment where people are happy to speak up, because otherwise you end up without your path being challenged, and that can lead you up the wrong way. The aviation industry has since about the 70s understood that aviation safety is affected by human factors, and Lufthansa's even developed this whole training academy where they train other industries in human factors based on their experience for pilots. They found that efficient communication, flat hierarchies, and situational awareness can all improve whether or not human factors can increase the safety of a flight. I'm just going to flick to a little video. I'll stop sharing my screen and share again. Okay, here we go.
It's on.
Is human. For this reason, we've made mistakes as we conquered frontiers. And with skies beckoning, we tried and tried to fly, but physics wasn't on our side. Then with a little bit of hot air, we finally beat gravity and powered right into the wild blue yonder. And it wasn't long before we slipped into the First World War. Amazingly, more people were killed by poor decisions and sloppy training than machine guns and dogfights. But with lessons learned, we blitzed our way through into the Second World War, and aviation began to streamline. More power, more dials, more speed. Sadly, introduced science, and the first rudimentary simulators started to trick reality. Then finally, the dust settled, and bombs were replaced by bums, and we soared passengers into the jet age. Pilots went from heroic risk-takers to wearing gold bars and wrangling with computers, and the airlines grew and grew. But so did the human factors, and they came thick and fast. And after several tragedies in the 70s, safety refocused, communication, and teamwork. And in the 90s, we really started to look at the whole picture, not just at work and second jobs, but at home and in play. So now we recognize that human error can occur anywhere, anytime, in any system. So as we build our knowledge of human behavior, we'll continue to boldly go where we've never been before. Each facet of human factors is interwoven with the other. If an organization doesn't invest in safety, it's impossible for people to be safe.
Aviation is often held up as the paragon of new technology and the future already here. And yet, it's only people, it's only the human who can hold together this complex, shifting patchwork of technologies, of communication requirements, of pressures and goal conflicts. It's only the human who can do that. If we don't understand the human factor, we don't understand safety and innovation at all.
Okay, I'm going to stop that little video there. Share my PowerPoint back. Okay, so they've long experienced human factors and they have a lot of training to help protect against human factors. The nuclear industry, that's a high-risk industry. Over 90% of nuclear accidents are attributed to human factors. They've had several high-profile disasters and near misses that have led them to focus on human factors. They do something called human reliability analysis and failure modes effects analysis. They apply human factors to actually the design of their plants, and they forensically investigate with respect to human factors. They have a special classification system, the Human Factors Analysis and Classification System. And like aviation, they train people to make the right decisions when faced with new circumstances. I think that's really important. It's very tempting in geotechnical engineering to have a whole load of standard operating procedures and processes that everyone has to follow. And that is great at delivering well on routine assignments. But when you have something different in front of you, you need to train people to make the right decisions in new circumstances. In the dams profession, the industry is only really recently beginning to recognise the importance of human factors. Someone called Alvey out of the US has looked at lots of dam failures and investigations and realises that dam safety can relate to the pressure from non-safety goals. So that's that goal blindness or commitment that we've talked about before. Human fallibility and limitations, so those are heuristics and cognitive biases, and the complexity of systems as well. The more complex the sort of human system around it, the more likely there are to be failures. And those are a few different dam failures that have had human factors implicated in them. Spencer Dam failure, one person died. Oroville spillway, that was an interesting one. That was an example of how an expert strayed outside of their area of expertise. So everyone followed them on that journey. So when they strayed and said something wouldn't happen, everyone believed that. And you can see that even going back to Viant, which caused over 2,000 deaths, has had human factors implicated in dam safety. So what do I think we can do to reduce the impact of human factors in our work? We can recognise that there are cognitive bias and heuristic traps, although that will only get you so far because research tells us that being aware of them is not enough to defend against them. We can emphasise communication. They certainly do that well in the airline industry in terms of human factors. And we need to create that environment where we encourage curiosity and speaking up, that you can challenge your experts, and that by encouraging that, you'll also create an environment where you're able to deal with new situations better. I think instigate a formal reflective process. So that would be where you had a pause, did some work, had a pause, and then went back to it a little later and challenged it. Was I right in my decision? Consider that you might be wrong, and deal with the uncertainty. Is there another answer or interpretation that's different to mine? If so, how would that impact my findings and recommendations? I do sensitivity analyses. We're very good at doing sensitivity analyses on our parameters. We're engineers, we love numbers. So if we had a friction angle of 30, let's try 28 and see what happens. But I very rarely see people do sensitivity analyses on their geological interpretations, which maybe could have more impact. Reduce the commitment pressure. That's the answer. That's reduce the pressure to come up with the answer that somebody wants to hear. We can use the evidence-based decision-making rather than judgment-based decision-making. I think judgment-based decision-making gets a sort of a bit of a fair press, but we need to really look at the data and use evidence-based decision-making, and that makes it defendable. Create cognitively diverse teams. We really don't want echo chambers. Staff projects adequately. Avoid complex responsibility matrices. It's been found that sort of flatter matrices guard a bit better against human factors. There's a willingness to speak up, which can be a cognitive bias. So use those flatter hierarchies within project teams, maybe. Use checklists. That's been found to be good. So if you're going out to inspect something, use a checklist to run through a series of questions for you. Use cross-checks or reviews. I mean, that's why most of us have a review process or an independent review process. In BC, for example, in high-risk projects, EGBC requires you to have a review process. And if they're very high-risk projects, that has to be someone outside of your firm or company. Develop risk registers and assessments. I think that helps you consider the uncertainty when you're working through that process. Audit systems and processes for human factors. Develop critical thinkers and practitioners that can deal with new situations. And share lessons learned. That can be something we're not great at. We all share really positive lessons, but when things go a little bit wrong, we have a tendency not to share them as much. So I've talked a lot about human factors, but we're moving into this AI age with machine learning. So what about those? Well, AI and machine learning are only as good as the data used to feed it. And training examples and human involvement in the provision and the curator of data that feeds into the AI are subject to bias. IBM said the models upon which AI efforts are based absorb the biases of society that can be quietly embedded into the mountains of data they're trained on. You can have algorithm bias, that's if you don't ask the question correctly. You can have confirmation bias when AI relies too much on pre-existing beliefs and trends and is unable to identify new patterns or trends. You can have sample or selection bias. You know, that's one we definitely have in geotechnical engineering, where the data used for training is not large enough. And you can have blind trust in the outputs. So the image on the right is an AI image. I asked it for an image of a piezometer in a dam, and this is what it came up with, which maybe I wouldn't have come up with myself. So don't have blind trust in the outputs. So that was sort of how we deal with it at work generally. I've thought of some specific examples where bias can creep into geotechnics. So site safety, especially with complacency and familiarity, we can learn from the avalanche experiences for sure. Geological interpretation, understanding and dealing with uncertainty, dealing with limited data or too much data and how we use or interpret or ignore some of that data. Particularly perhaps with parameter selection, understanding how our sampling method of transport may impact our samples test or cause. For example, that might be a uniaxial compressive strength test in a rock core. In order to take a test in a rock core, for UCS, you need a minimum 2-to-1 ratio of length to core diameter. So by the very nature of selecting that, you actually select the strongest rocks because the other rocks are likely more fractured. So if you're selecting those larger cylinders from your core, you're already biasing your data, and you should understand that. Assumptions about material models, you know, linear strength models, rocks. I often see slope stability models where people have just assumed the rock is an impenetrable boundary, and that may not be the case at all. We often assume that what's missing is the same as what we have investigated, and that's often not true. We extrapolate relationships beyond the extent of those relationships. One example of that would be the LEPS curve for rock fill, where in the mid-70s, LEPS came up with this strength curve for rock fill, but it was based on a fairly low stress environment. And now in the modern world, we extend that LEPS relationship way beyond the stresses that it was originally built for. We can have false confidence in our data and our interpretation. And in analyses, we can creep bias into our analyses. So here, just a few slides with examples of this. This is an open pit. There's a pit shell in there. You can just make out the pattern. And those are all the boreholes. It looks like a lot of boreholes. It is a lot of boreholes. But we're still exploring very little percentage of the ground. So there's still uncertainty in there. We tend not to account for that uncertainty in our designs. So another on the theme of we explore very little of the ground. This is actually work that came out of the UK back in the 90s on contaminated land. Contaminated land is a bit different to geology because you might have some theories about what the geology is doing before you go in, whereas they can often be looking for more random occurrences. But they looked at grid patterns for boreholes. And whilst a square grid, G, on the top left graph, is quite efficient at looking for circular targets, when you start looking at ellipses in the bottom left, so that would be the E, that might be a buried channel, a buried river channel. A square grid is not actually very efficient at picking it up. And you need to be moving to what they call an offset herringbone grid. I rarely see herringbone grids in geotech. Everyone goes straight for a square grid, but it's not very good at picking up these longer, thinner things. And we may have geological reason for these longer, thinner things. So maybe think about your grid. I understand why herringbone isn't preferred because it's difficult to set out on site, but just think about what you might, your borehole layout plan, how that may or may not miss things, and whether those things it may or may not be missing are geologically possible or likely even. We often interpret between investigation points, right? Or nowadays we let a machine interpret for us. This is a leapfrog model on the right hand side. And we tend to interpret between investigation points with a series of rules that we have set, whether we're doing that by machine or by hand. We tell it how to extrapolate between two boreholes. And we need to think about whether we're doing that correctly. Then when we go to analyses, this is just a GeoStudio analysis on the right-hand side. We set rules for our analyses and our packages, and we assume our rules are correct. So particularly that might be, are you using the appropriate search function when you look for your stability? You might use entry and exit, you might use grid and radius, but you might need to go for block functions if you're looking at weak thin layers rather than entry and exit or block. It'll only find the worst case within the set of rules that you prescribe it. So you need to think about those set of rules. So in conclusion, humans are susceptible to heuristics, expert halo, and cognitive bias. They impact other professions, and they can impact our own profession of geotechnical engineering. Consider cognitive bias and heuristics in your daily practice and reflect on where it can creep in. And maybe develop some strategies, and I've suggested a few to deal with the potential for bias heuristics. And on the right is, I told AI to do buffalo jumping off a cliff and dying, but that's an example of AI not quite getting it right because I just couldn't get all the buffalo on the toe of the slope to die. But buffalo jumping off a cliff is an example of bandwagon, where you're just blindly following the crowd, believing it's the right thing to do. So I'd like to thank you for listening and coming along my human factors journey with me. I've written a few papers, I've got them up here if anyone wants to go out and read a bit more, and I will be presenting a short course at a conference workshop this year as well. But there should be time for questions, and thank you for listening. I hope you found it useful.